Ever wondered if the universe itself is a giant, incomprehensible puzzle? What if I told you that we're not just figuring out the pieces, but also learning how to speak the language in which the puzzle is written? That language, my friends, is quantum mechanics, and the key to unlocking its secrets might just lie in the power of quantum computers. Schrödinger's equation, a symphony of symbols that paints a vivid picture of the quantum world, is the very backbone of quantum mechanics. It acts as a roadmap, revealing how particles evolve, interact, and how probabilities shape the reality we experience. Without this equation, our understanding of the universe at its most fundamental level would simply crumble. Imagine taking this powerful equation and using it not just to observe the universe, but to actively build with it. This is the tantalizing promise of quantum computers, machines that aren't bound by the rigid rules of classical computing, but instead think in the fluid, probabilistic language of reality itself. One from theory to reality, the birth of a quantum dream. But how did this revolutionary idea come about? The story starts in 1980 with a physicist named Paul Benioff, whose mind dared to venture beyond the limitations of classical computers. He envisioned a machine that didn't rely on ordinary digital bits, but on qubits, tiny units that danced to the tune of quantum mechanics. This quantum Turing machine was the first concrete step towards the quantum computing we know today. At the time, Benioff's idea seemed more like science fiction than a practical possibility. Classical computers were constantly improving, but when physicists tried to use them to simulate quantum systems, they hit an impenetrable wall. The issue wasn't simply a matter of speed. Classical computers couldn't handle the exponential complexity inherent in quantum physics. Think about it. To simulate even a small molecule accurately, you need to account for the interactions of every electron, every atom, and every possible configuration. The number of calculations explodes exponentially with each added particle, quickly overwhelming even the most powerful supercomputers. This daunting challenge attracted the attention of two other brilliant minds, Yuri Manin and Richard Feynman. They both independently suggested a radical solution. To truly understand quantum systems, we needed computers that worked like them. That meant building computers that could harness superposition and entanglement, the strange and wonderful phenomena that define the quantum world. 2. Quantum cryptography, protecting secrets with the laws of physics. Richard Feynman's pioneering ideas continue to inspire innovation. In 1984, Charles Bennett and Gilles Brassard took the quantum world's bizarre principles and applied them to something truly revolutionary: cryptography. They realized that the peculiar behavior of particles, like photons, could be used to create a communication system that was not just secure, but fundamentally unbreakable. This concept, known as quantum key distribution, QKD, turns the very rules of quantum physics into a practical tool for protecting secrets. Imagine Albert and Catherine, two individuals trying to exchange a private message, knowing that an eavesdropper, let's call her Ella, is lurking. Using the Bennett-Brassard method, Albert sends Catherine a string of photons, each representing a bit of information, a 0 or a 1, encoded in its quantum state. This is where the magic of quantum mechanics comes into play. If Ella attempts to intercept these photons, the very act of measuring them changes their states, leaving undeniable evidence of interference. To ensure their communication is secure, Albert and Catherine publicly compare a small portion of the photons to check for errors. If the measurements match perfectly, they know their key is safe and can be used to encrypt their message. If not, they abandon the key and start over, knowing that any interference will always leave a trace. This process is remarkably secure because it relies on the laws of physics, not on computational complexity. Even the most powerful quantum computers cannot break this encryption, because any attempt to eavesdrop will inevitably alter the quantum state of the photons, alerting Albert and Catherine to the intrusion. Think of it like trying to sneak a peek at a book without opening it. The very act of trying to look at the quantum information inevitably disturbs it, like a ripple in a pond revealing your presence. Bennett and Brassard's work was a giant leap forward, proving that quantum mechanics wasn't just a theoretical concept confined to laboratories. It could shape the future of technology. Today, QKD is already being used in sensitive industries, from government communications to financial systems, ensuring secrets remain untouchable even as the world marches toward the age of quantum computing. It's a testament to the power of harnessing the fundamental laws of the universe to protect our information in an increasingly digital world. Have you ever considered the implications of quantum cryptography for securing your personal data in the future? 3. Classical versus quantum, a tale of two computers. Classical computers, the workhorses of the modern world, have undeniably transformed our lives. They power the internet, send humans to the moon, and allow you to watch this very video. But let's be honest, when it comes to tackling some of the universe's most complex problems, they're simply outmatched. That's where quantum computers step in. They don't just calculate, they think differently, using the very rules that govern the universe itself to unlock possibilities no classical computer could ever hope to touch. Classical computers process information in bits, zeros, and ones, like flipping a series of tiny light switches on and off. Think about weather prediction systems. They use massive computational models that break down atmospheric data into binary representations. Temperature, pressure, humidity, and wind patterns are all converted into binary code. The same is true for digital photography. When you take a photo with a digital camera, the image is captured as millions of pixels, each represented by a series of bits. Every computation they perform is essentially a long series of these bits flipping in precise patterns. While this approach is effective for many tasks, it becomes painfully slow when problems become complex, like simulating molecules, solving optimization puzzles, or cracking encryption. The reason is that classical computers are stuck solving one possibility at a time, step by step, even if they do it incredibly fast. It's like trying to find the right key in a huge pile of keys by trying each one individually. Quantum computers, on the other hand, play a completely different game. They process information in qubits, which can exist in multiple states simultaneously thanks to superposition. Imagine trying to guess a 4-digit PIN. A classical computer would test each possible combination one at a time, 0, 1, 2, and so on, until it finds the right one. A quantum computer, however, could test all 10,000 combinations simultaneously, zeroing in on the correct answer almost instantly. This ability to consider all possibilities at once is what gives quantum computers their incredible advantage. And it doesn't stop there. Quantum computers also utilize entanglement, where qubits become linked in such a way that the state of one qubit instantly influences the state of another, no matter how far apart they are. This interconnectedness allows quantum computers to process and analyze data in ways that classical computers simply can't. It's like having a team of genius problem solvers who can instantly share insights with each other, working together seamlessly to tackle challenges that would take a classical computer millions of years. A single qubit isn't just a new way to store information. It represents a connection to the vast possibilities of the quantum world. With just 300 qubits, a quantum computer can represent more states simultaneously than there are particles in the observable universe. Think about that. Every atom, star, and galaxy combined doesn't even come close to the computational possibilities of a moderately sized quantum computer. Do you think that this kind of potential can change our world faster than we can imagine? 4. Why quantum matters. applications that could change the world. So, why does all of this matter? Classical computers struggle with problems that grow exponentially, like simulating chemical reactions. A molecule with just a few dozen atoms might require more classical computing power than exists in the world. Quantum computers, however, can handle this complexity with ease, using their ability to explore multiple states at once. This has huge implications for drug discovery, material science, and understanding the building blocks of life itself. Imagine being able to design new drugs with atomic precision, creating materials with unprecedented strength and conductivity, or finally understanding the complex processes that drive life at the molecular level. These are just a few of the possibilities that quantum computing unlocks. And then there's cryptography. Classical computers protect our online world using encryption systems like RSA, which relies on the difficulty of factoring large numbers. A classical computer would take millions of years to crack these codes. 5. The encryption game, breaking the unbreakable. Breaking internet encryption like RSA can seem complicated, but the core principle is surprisingly straightforward. Imagine you're shopping online for a book and need to enter your credit card details at checkout. RSA encryption protects this information. When you hit submit, your browser uses the bookstore's public key to encrypt your credit card details. Think of it like locking your information in a box. The bookstore has the only key, its private key, to unlock that box. Even though this locked box travels through the internet, only the bookstore can open it. However, if someone studied the lock carefully enough, they could figure out how to make a key and break in. The question is, how long would that take? The security of RSA depends on large prime numbers. The public key is shared with everyone, but the private key is kept secret by the bookstore. What makes RSA strong is how hard it is to figure out the private key from the public key. This difficulty comes from factoring a big number into two prime numbers. For example, the number above, called RSA 2048, was created by RSA Security, LLC. The largest RSA number successfully factored to date was 768 bits in length, an achievement that required computational effort equivalent to 2,000 years of computing power distributed across multiple machines. However, a quantum computer running Shor's algorithm could crack RSA encryption in a matter of hours or even minutes. This isn't just a theoretical advantage. It's a wake-up call for the future of cybersecurity. Should someone discover an efficient algorithm for solving the integer factorization problem, it would shatter the foundation of current internet security protocols. Shor's algorithm is a quantum method that can solve this problem efficiently, something previously thought impossible. That's why it's such a big deal in the world of cryptography. Are you prepared for a world where current encryption methods are rendered obsolete? 6. Beyond encryption, optimization and the quantum edge. Optimization is another area where quantum computers shine. Think about routing delivery trucks, scheduling flights, or even managing traffic flow in a busy city. Classical computers can only make educated guesses at the best solution, but quantum computers can analyze all possibilities simultaneously, finding the optimal path in seconds. This isn't just about convenience, it's about efficiency, saving energy, time, and resources on a massive scale. Imagine the impact of optimizing global supply chains, reducing fuel consumption in air travel, or minimizing traffic congestion in urban areas. Quantum computers could unlock unprecedented levels of efficiency in these systems, leading to significant economic and environmental benefits. 7. The quantum catch. Not a silver bullet, but a powerful tool. Quantum computers might seem like the answer to everything, but as incredible as they are, there's a catch, a big one. Quantum computers aren't a universal fix for all problems. In fact, for many everyday tasks, they're completely useless. They're not built for the kind of tasks we rely on classical computers for, like checking your email, streaming a video, or running simulations for video game physics. These are deterministic problems with clear step-by-step solutions. Classical computers are perfect for this because they excel at running instructions in sequence quickly and efficiently. A quantum computer wouldn't just be overkill for these tasks. It would be painfully impractical. The technology needed to set up and run a quantum system is so complex that it's like using a spaceship to drive to the grocery store. It's simply not the right tool for the job. Even when quantum computers are useful, they come with unique challenges. Remember how they calculate all possibilities at once. That's true, but when you measure the result, you don't instantly get the perfect answer. Instead, you get a probabilistic outcome. The quantum state collapses, and what you observe is just one of the many possible results. This means you might have to run the same computation multiple times to get a reliable answer. Without carefully designed algorithms to amplify the correct solution, all that raw quantum power is wasted on randomness. And then there's the issue of fragility. Qubits, the building blocks of quantum computers, are incredibly sensitive. They exist in a delicate state, easily disrupted by heat, vibrations, or even the slightest electromagnetic interference. When that happens, the quantum state collapses and the computation fails. To prevent this, quantum computers require extreme conditions, temperatures near absolute zero and isolation from any outside noise. Maintaining these conditions isn't just challenging, it's expensive and resource-intensive. Error correction is another hurdle. Because qubits are so fragile, errors happen often. Fixing these errors requires additional qubits to act as backups, which means the actual number of qubits needed for useful computations is far greater than it seems. For example, while a problem might theoretically require 1,000 qubits, the error correction process could push that number to millions. Building a quantum computer of that scale is far beyond our current capabilities. And let's not forget about scale and accessibility. Most of the quantum computers in existence today are prototypes, capable of handling only a few dozen qubits. For instance, Google's Sycamore platform, developed by Google Quantum AI, is primarily used for cryptography research. Similarly, Rigetti Computing's Aspen M3 platform focuses on advancing quantum chemistry simulations and accelerating machine learning tasks. These examples highlight how quantum computing navigates its early developmental stages, with much progress needed before widespread application becomes feasible. For quantum computers to tackle the kinds of problems we dream about, like breaking encryption or simulating complex molecules, they'd need thousands or even millions of stable, error-corrected qubits. Right now, we're a long way from reaching that milestone. Quantum computers are also highly specialized. They excel at certain types of problems, like factoring large numbers or solving optimization challenges, but they're not general-purpose machines. If a problem doesn't align with the strengths of quantum mechanics, a classical computer will likely be faster and more practical. For most of the tasks that keep the modern world running, classical computers remain the best tool for the job. Are you surprised to learn about the limitations of quantum computers? 8. The quantum future, a complementary revolution. So no, quantum computers aren't the answer to everything, but that doesn't make them any less extraordinary. Their real potential lies in solving problems that are fundamentally beyond the reach of classical systems. They won't replace classical computers, but they will complement them, tackling the hardest and most complex challenges. Things like understanding the universe, discovering new drugs, or creating materials that don't yet exist. They're not about making life more convenient. They're about expanding the boundaries of what's possible. In the end, quantum computers are tools for the extraordinary, not the everyday. They won't stream your favorite show or run your favorite app, but they might help us unlock the secrets of the universe itself. And that, in its own way, is more than enough. 9. The enigmatic quantum world, a source of confusion and wonder. Nobody understands quantum physics. This classic quote reflects the profound challenges and inherent strangeness of the quantum world. There's no shortage of similar sentiments from some of the greatest minds in physics. Those who are not shocked when they first come across quantum mechanics cannot possibly have understood it. Niels Bohr. Quantum mechanics makes absolutely no sense. Roger Penrose. If quantum mechanics is correct, it signifies the end of physics as a science. Albert Einstein. I do not like it, and I am sorry I ever had anything to do with it. Erwin Schrödinger. Isn't it somewhat comforting to know that even the brightest minds grappled with this subject? Yet here we are, supposedly not letting their confusion guide our tech predictions or philosophical views. But let's face it, aren't we all in some way influenced by the enigma these giants couldn't fully grasp? Fast forward to recent years, and while quantum mechanics is still a challenge to wrap your head around, we're now using it to build powerful tools like quantum computers. Google recently made headlines with their new quantum chip, Willow. It's a 105-qubit chip that's making huge strides in error correction, one of the biggest hurdles in quantum computing. The reason this matters is because quantum systems are fragile, and even the smallest disturbances can mess up calculations. Willow tackles this by improving error correction as more qubits are added, making it more reliable and practical for real-world use. But how practical exactly? Willow solved a problem in under 5 minutes, not just any problem, but a problem that would take the world's fastest supercomputers longer than the age of the universe to finish. It's not just a flashy experiment either. This kind of power can be used to tackle real-world challenges like designing new materials, optimizing supply chains, or developing life-saving drugs. Are we on the cusp of a quantum revolution that will reshape our world? 10. AI versus quantum. Collaboration, not competition. At the same time, artificial intelligence has been dominating headlines with its own breakthroughs. AI's strength lies in its ability to learn from data and solve complex problems, like DeepMind's AlphaFold, which figured out how proteins fold, a problem that has stumped researchers for decades. AI is fast, adaptable, and surprisingly good at handling tasks once thought impossible. But quantum computing is different. It doesn't just solve problems faster, it tackles problems classical computers, even with AI, can't handle at all. It uses the strange principles of quantum mechanics, like superposition and entanglement, to process information in ways that classical systems simply can't match. This is what people mean by quantum advantage. That said, AI has started to encroach on some quantum computing's territory. By training on huge datasets and incorporating physical rules, AI has shown it can often get similar results without needing quantum hardware. Experts like Demis Hassabis of DeepMind suggest that, in some cases, AI might be able to solve problems that we once thought only quantum computers could handle. If that's true, the practical uses for quantum computing could be more limited than we initially thought. But the real story isn't about one replacing the other. It's about figuring out where each excels. AI is great for many types of problems, but as problems grow more complex, quantum computing becomes a better tool. Instead of seeing them as competitors, it's more helpful to think of them as complementary technologies. Both are reshaping how we solve problems, and together they're opening up new possibilities in science, medicine, and beyond. Do you think that AI and quantum computing will change our lives a lot soon? 11. Wormholes in the universe as a quantum computer. In late 2022, physicists made headlines by simulating wormhole-like behavior using Google's Sycamore quantum processor. This was not a physical wormhole. No tunnel through spacetime connecting distant points was created. but the experiment provided a fascinating window into how information might behave in scenarios akin to traversing a theoretical wormhole. The experiment centered on quantum entanglement and teleportation, two key principles of quantum mechanics. The researchers sought to recreate the dynamics of a wormhole, as described in the theoretical framework of quantum gravity. They implemented a simplified model known as the holographic principle, which proposes that our universe's higher dimensional reality could be described as a projection of lower dimensional physics, similar to a hologram. By encoding quantum states into the processor and manipulating them with carefully designed algorithms, the team was able to simulate the transmission of quantum information in a way that mirrored theoretical descriptions of wormhole dynamics. Similarly, they observed phenomena that aligned with how information would travel through a wormhole in spacetime, according to Einstein-Rosen bridge models. The experiment was groundbreaking because it bridged concepts from quantum mechanics and general relativity, two pillars of modern physics that are notoriously difficult to reconcile. While this simulation didn't create an actual wormhole, it demonstrated the potential of quantum computing as a powerful tool for exploring some of the universe's most enigmatic phenomena. When you look at the principles of quantum mechanics, superposition, entanglement, and interference, it's hard not to see the parallels. A quantum computer processes information by exploiting these principles, solving problems in ways that classical computers simply can't. Similarly, the universe operates on these same rules at its most fundamental level. Particles don't have fixed states until observed. Quantum systems influence one another instantaneously over vast distances, and probabilities drive outcomes. It's as if the universe itself is running a cosmic program, calculating its evolution moment by moment. Physicist Seth Lloyd once suggested that the universe might indeed be a massive quantum computer, with every interaction between particles acting as a fundamental computation. In this view, everything we observe, from the motion of galaxies to the spin of an electron, is part of an ongoing quantum calculation. This perspective isn't just a metaphor, it's a way of understanding the universe's complexity. A quantum computer doesn't solve problems in the linear, step-by-step way that classical computers do. Instead, it considers multiple possibilities at once, much like how the universe seems to explore all potential outcomes before collapsing into a single reality. If quantum computers can simulate wormholes, why couldn't they simulate the universe itself? The wormhole experiment on the Sycamore processor becomes even more profound when seen through this lens. It wasn't just a simulation of a theoretical phenomenon. It was a demonstration of how the same principles that govern the universe can be replicated in a machine. By recreating these dynamics, physicists are essentially building a tiny, controlled version of the cosmos. This is why quantum computing is so revolutionary. It doesn't just perform calculations, it mirrors the universe's own processes, offering us a way to study reality itself in unprecedented detail. The implications of this are staggering. If the universe is a quantum computer, then every particle, every force, every interaction is part of an elaborate computation. This idea not only reframes how we think about the cosmos, but also suggests that by understanding quantum computing, we might unlock the deeper logic behind existence itself. Simulating wormholes is just the beginning. Quantum computers could one day model black holes, dark matter, or even the birth of the universe, giving us tools to answer questions that have eluded scientists for centuries. What makes this all the more fascinating is how natural it feels. The principles of quantum mechanics align perfectly with the processes we observe in the universe. It's as though the universe was designed to be understood this way, using the same mathematical language that quantum computers speak. Every breakthrough in quantum technology brings us closer not just to solving practical problems, but to understanding the nature of reality itself. 12. The simplicity bias. Are we missing the bigger picture? They say the universe is written in the language of mathematics, but even the cosmos has its limits. Take a coin and flip it. Did you get heads? Flip it again. Heads again, tails, keep going. Is that your result? Probably not. That seems obvious, but why? There are about 1 million different ways a coin can land in 20 flips. The odds of getting the exact same sequence of heads and tails as someone else is 1 in 1 million. You'd have better luck playing the lottery, though let's be honest, you probably won't win that either. Now imagine flipping the coin 100 times, or let's say 266 times. With 266 flips, the total number of possible sequences is bigger than the commonly cited estimates for the number of atoms in the observable universe. For a single coin flip, there are 2 outcomes, heads or tails. For n flips, the total number of possible sequences is 2 to the power of n. That means for 266 flips, this would be 266, which is this massive number. So what if we counted them 1 per second? You couldn't do it alone, but what if everyone on Earth helped? Let's say there are 10 billion people. Nope, still not enough. What if each of those 10 billion people had a computer that could count 10 billion sequences per second? Still no. Alright, let's imagine there are 10 billion planets like Earth, each with 10 billion people, and all of them have computers counting 10 billion sequences per second. That's a lot, right? But no, it's still not enough. Now let's go even bigger. Imagine 10 billion galaxies, each with 10 billion planets, each planet with 10 billion people or computers, counting 10 billion sequences every second. Still not enough. Even if we stretch this across 10 billion universes, all with those same galaxies, planets, people, and computers, it would still take 100 times the age of all those universes to count every possible sequence from 266 coin flips. Why am I telling you this? The point is simple. The notion that humans are inherently drawn to simplicity in a universe that's fundamentally complex is a profound observation. It touches on cognitive biases, the nature of scientific inquiry, and the limitations of technology, including both classical and quantum computers. This bias towards simplicity is evident when we consider how we've historically approached scientific problems. We've developed models and theories that explain phenomena in the simplest terms possible, not necessarily because the universe itself is simple, but because that's what our cognitive framework can process. We humans love finding patterns, and that makes us think life, nature, or the universe is simple. But it's not. It's actually really complicated, like someone searching for their lost keys at home under a streetlight just because that's where the light is. We only notice the simple things because that's all our brains can handle. But the truth is, the simple stuff is the exception, not the rule. Let's try an example. Imagine I ask you to figure out the outcome of 266 coin tosses. Sounds impossible, right? After all, I just explained that there are so many possibilities you couldn't even write them all down. How could you possibly pick just one? Fair point. But here's the thing. You have a coin in your hand and 10 minutes to spare, so you start flipping. As you work through it, you realize something interesting. You're basically acting like a computer. You took an input, followed a set of steps, an algorithm, and then produced an output. Problem solved. Now imagine trying to simulate 266 coin tosses. But this time, each toss depends on all the previous ones in a completely unpredictable way, like the coin has a huge memory bank. To figure that out, you need to keep track of every possible combination, which, as we already know, is beyond impossible. Well, not impossible, just incredibly, ridiculously time-consuming. But here's the kicker. Figuring out how each toss depends on the others is even harder. In fact, it's so complex that it's uncountable. There's one situation, though, where things are much simpler, when each toss is completely independent of the others. That's the version we're familiar with. Why? Because it's the only one we've learned how to solve. It seems obvious to us, but only because it's manageable. The problem is manageable because we only deal with probabilities and not interdependencies. Life, as it turns out, is usually messy and complicated unless we stick to the easy stuff. Computers, for example, essentially produce sequences that look like coin flips. They do this by flipping transistors on and off, creating bits of data. But here's the catch. Your computer will never produce every possible sequence of bits. It sticks to the simpler ones or it crashes. That is why, when we try to model more complex systems like weather patterns or biological processes, computers struggle. Because these systems are inherently dependent on countless variables interacting in nonlinear ways. There's nothing magical about computers that makes them work this way. It's just that we design them to solve problems we know how to handle. We keep them on a narrow, simple path because we built them to solve what we, as humans, find doable. Computers are only as smart as the simplicity we force them to stick to. Do you agree that we can only create machines as smart as we can design? 13. Quantum computing. Managing complexity, not eliminating it. Quantum computing isn't much different from anything else. It's complicated, but we focus on problems we know how to solve, like flipping quantum coins. While quantum computers leverage quantum mechanical phenomena like superposition and entanglement to potentially handle certain calculations more efficiently, like factoring large numbers for cryptography, they are not universal solvers for all complex problems. A quantum computer won't be a magical machine that solves every problem by handling more variables than there are particles in the universe. It will only solve the problems we've designed it for, because those are the ones that can be tackled with the resources we have. We don't need to manage every detail of quantum systems, just like your regular computer doesn't track all the possible ways it could be configured. So the next time someone says quantum computing is too complicated because of all the possibilities, remember that nature itself is complex. The complexity of the universe isn't reduced. Rather, we find new ways to map some of that complexity into problems we can solve. Without our current technology, our understanding of the universe is contingent on the tools and cognitive frameworks we have. We simplify to comprehend, but in doing so, we must recognize that we're often dealing with only a sliver of reality. The universe's complexity isn't an obstacle to be overcome, but a fact to be acknowledged. Our technological advancements, including quantum computing, help us manage this complexity in specific, controlled environments, but they don't eliminate it. While the quantum age is approaching, we're still in a phase where misconceptions are common. Moving forward means focusing on understanding the science, not the myths. So what have we learned? We've seen how quantum mechanics, once a source of bewilderment for even the greatest minds, is now being harnessed to build revolutionary technologies like quantum computers. We've explored the potential of these machines to solve problems that are beyond the reach of classical computers, from drug discovery to encryption. We've also acknowledged the limitations of quantum computing, recognizing that it's not a silver bullet but a powerful tool for specific tasks. Most importantly, we've recognized the inherent complexity of the universe and the human tendency to simplify things to make them understandable. This simplification can be a powerful tool, but it's important to remember that we're often dealing with only a sliver of reality. As we continue to explore the quantum world, it's crucial to approach it with a combination of wonder, skepticism, and a willingness to challenge our own assumptions. The universe is a vast and complex place, and our understanding of it is constantly evolving. By embracing this complexity and continuing to push the boundaries of our knowledge, we can unlock new possibilities and gain a deeper appreciation for the mysteries of existence. And finally, remember to find a balance between the wonders of the quantum world and our everyday lives. Use the lessons learned to be more curious, creative, and understanding of the world around us. It is an extraordinary world. And what about you? What are your thoughts on the future of quantum computing? Do you think it will revolutionize our world, or are its limitations more significant than its potential? How might this shift affect our lives, our jobs, or our understanding of the universe? Let's start the discussion. Wishing you excellent health. If you enjoyed this exploration of quantum mechanics and its profound implications, please subscribe to our channel for more thought-provoking content. Together, let's delve deeper into the fascinating mysteries of our universe and unlock the secrets that await